All right, let's go ahead and jump back to verilog. Hopefully y'all remember last class when we talked about gates. Everyone feels great about gates, right? Y'all love gates. It's wonderful. All right, so let's do a quick review. I guess, how long does it take this gate to saturate? Or what's the gate delay? I haven't added it yet.
3.
We got 3, okay. Any other guesses?
2. 4.
2, 4. All right, so who wants to defend their number? You'll defend yours? Go for it.
So the and on top takes 2.
Mm-hmm.
And then the not on bottom takes 1. So, but it still has to wait on the and in order to go to the or.
Wait. Wait, who's waiting on what?
The not is waiting on the and.
No, there's no, the output of the and doesn't go to the not.
No, yeah, I meant in order to go to the or.
Okay.
It's waiting. It has to wait on the.
Oh, okay, so or, you mean
Yeah,
or is waiting on the
waits,
output of
has
these
to wait
two.
on both
Right.
the and the not.
Right.
To go, and so it's and plus or is 4.
Oh, and plus or, thank you. Yeah, so that's, which is 4, correct. To be more clear, I should say, the not and the and happen in parallel because they don't depend on one another. So they happen in parallel, but the or is waiting on both of them, so it has to wait on whatever's the longest path, which is 2. So it has to wait for the and to saturate, and then the or takes another 2, so it's 4. So in other words, it takes 4 gate delays to get to the x and only 1 gate delay to get to the y. And so you need to wait for all of it. So the highest one, of course, is the x. All right. All right, good review. All right, great. Let's see. So we started talking about verilog. We didn't do any coding, did we? No. Okay, perfect. So the first type of verilog is called structural, and I think I started to go over this, but we'll go over again. And oh, I just remembered I completely ignored you when you asked about Scrum do. Remind me at the end of class. There we go. So back to structural. So in structural mode, which is the way you should be using verilog for this class, except for your test cases. When you write your normal code, it should be in structural. When you write your test cases, it should be in behavioral. Yes, and you will want to write many, many test cases, trust me. It's not, you're going to be very sad if you don't. But in structural, first you declare, well, you're going to have already A, B, and C declared, as well X and Y due to how a module is set up. So you already have those wires. But in this version, you're going to need one more wire that goes from the and to the or, and that's why we call it E. Doesn't make too much sense right now. Just know that we have to label our wires, and it should make a little more as we move along. In structural, you then state where all the gates are. So you have AND gate, which takes, and when you do AND, you first label the output. So we're going to output E right there. I'm going to use the mouse pointer for the online student. Outputs E right there, and the 2 inputs are A and B right up here. And we labeled it gate 1. By the way, this is superfluous. You don't actually need to label it, but it's going to be very handy for when you test it, so I highly recommend that you label them. And then the #2 just signifies that an AND gate takes 2 clock cycles in order to complete. You could change that in the morning in case someone magically came up with a better way to do AND. It could happen, but for our class, we're just going to assume an AND takes 2 cycles. Down here with the not, the output is Y because it's going to be piped directly to the Y. The input is C. There's C coming in. We call it gate 2, and it's a not, and it takes 1 gate delay. We have an OR up here. The output's the X. There's the X, so you label it first. And then you have the 2 inputs. One's the E, which came from the AND, and the other is a fan out of Y. So this is legal right here, where you can have a line that fans out. We're not EE guys, that's okay, but does anyone see issues with fanning out? So think a very good analogy for electricity is just think of water flowing through a pipe, and your voltage is how much pressure the water has. Amperage is basically how wide that pipe is and how much you can get through. It's not a perfect analogy, but it's pretty good. It's pretty good. So if you have a pipe going here, and then all of a sudden you cut the pipe in half, what happens to your pressure?
It goes down.
It goes down. And if you remember your transistors, you have to have enough voltage in order to change the transistor. So if you fan out too many times, you'll lose voltage. And then in that case, you will have to put extra logic here in order to up the voltage, which does increase your gate delay. We are never going to worry about that. All right? But I wanted to point that out because that's the EE guy's job, not us. He goes figures that out. We're just trying to get the logic correct. But do keep that in mind that there's a lot more to this than just us putting gates inside of Verilog and hitting go. Okay, everyone good with structural? All right, the next one, they call it behavioral, but the one over here is called data flow. Notice it's an assign. We're assigning E to be A and B. Hey, look, it looks like C. And a lot of y'all may want to write it in data flow, but stick to structural for now. One, because that's what I'm going to grade you, and two, this is too much of a crutch right now, I guess is the best way to put it. And then again, assign what Y is going to be, which is just the not C, and assign what X is going to be, which is X, E, or Y. Now, a good Verilog compiler can translate this into that. That one's not too bad. The next one is where it gets very, very tricky. So you have registers E, X, and Y. We haven't even talked about registers yet. A register is a piece of memory. So, and right now we're in Verilog, so unless we label otherwise, a register has 1 bit. So E is a register. That means that it will hold the value across, well, just always hold the value for now. We haven't talked about other things yet. This is important because you have X, Y that needs to hold the output, and then we need to have E, which will be for behavioral mode, will need to hold the output. But notice that we don't actually need to hold the output. In here we have an always block. When A, B, or C changes, so in other words, when A, B, and C change, run this piece of code. So when this happens, A, B, or C change, run the code. You have begin and end. You can think of that as open curly bracket for begin and close curly bracket for end. And then you assign each value just like in C. A lot of y'all are going to want to do behavioral because it's basically C, is what it is. But it's not going to help you in understanding how circuits work, and plus I'm going to grade you on structural anyways. But if you want to test it, by all means write behavioral so you can come up and write a test case real quick. All right, those are the 3 modes. They labeled in the slides these two as behavioral, but it's really structural, data flow, behavioral. How are we doing? Okay. Let's see if I can, let's look at some code real quick. I think I wrote this already. Oh, sweet. And how hard is that to see? Huh. Well, that's interesting. Let's see if I can move that down. Is that still really hard to see? Wow, the M is out. Okay. How are we doing now? Or will this be better? Is that better? Worse? Better? All right, let's see if we can make it bigger. Let me also see if I, because it doesn't quite fit on my screen right. There we go. Oh yeah, how do I make this bigger? I haven't used this in a long time. Oh, that's cute. Wow. Huh. I don't want to use gedit. All right, let's try gedit. Do I not have gedit? I do. What does this thing do? Oh, we want to create that. I can insert an emoji? Sweet. All right. I think you're just going to be out of luck for now.
Yes.
Okay, that's better than it was. All right, so we're going to stick with that. Okay, so that was going to be hard because it's not VI. Whew. All right, I can do this. So module, simple. All right, very common in Verilog to put everything inside of a module. You can think of a module as a class, although it's not, you don't actually have functions. So it makes more sense to call it a struct. Did y'all do structs in procedural? All right. Yeah, you did struct. So think of a struct slash module or class, but a class without functions. And so you're naming a type, and the type we're going to call it simple, because the simple is going to represent this entire circuit right here. So when you declare a module, you need to declare what its inputs are. So you have inputs A, B, C, and its outputs X, Y. And you just label them. I prefer to put the inputs first and the outputs last. You can do it the other way, but you better make sure you remember that order, or it's going to get very weird. So I just label them A, B, C, X, Y. Excuse me. And in Verilog, you just give them the labels right off the bat, and then afterwards you tell them what their type is. So I'm going to call A, B, C input wires, A, B, and C. So those are wires going into the module. And then down here, output wire. So those are wires coming out of the module. We're good so far? We declare our internal wire here, E. And then here's the AND, NOT, and OR gates, which are the same thing as written over here in structural. All right, y'all see how I package that together? And so, I don't know what I saved, but okay. If you do iverilog on simple.v, oh good, no problems. Iverilog does produce a a.out file, and if you run it, nothing happens. Well, yes, because just like in C, you can make it do a bunch of work, but if you don't print anything, obviously it's not going to tell you anything. So we need to come up with a way to print it. And this is going to get a little weird at first. So we'll do, what was it called? Simple-test. All right. Again, you need to wrap it in a module. Since it's a test module, you don't have inputs and outputs. That doesn't make any sense. You're just testing something. So we're going to create a module called simple test, and we're going to create some registers. I haven't talked too much about registers, but a register is, you can think of it as inside of a test module, is a source of some value. We want to start a value and have it come from somewhere, so we have to have a register for it. Input 1, input 2, input 3. Hey, those are the 3 inputs to our simple circuit. And then a wire called X and Y, which will be the output. So, and if we go down here, the first thing we do is we call simple. Remember, that's our command or our module called simple. So we're instantiating a simple. Notice that you can instantiate as many of these as you want, just like a class or a struct. But we're just going to do one because we're just testing it. It is very common to call it DUT. Any guesses on that TLA? Do you know what TLA is? 3-letter acronym.
I think I remember what it is, but I don't know if you want me to answer.
Go for it.
Device under test.
There we go. Very common in E, device under test. N1, N2, and 3, notice that those are the registers going in, and X and Y, those are just straight wires coming out. So it's going to wire up the output of the registers into our simple module, and then the output wires are going to be assigned to X and Y. All right, initial begin. Initial means that when the simulation starts, start here. Begin and end, those are just like open curly bracket, end is close curly bracket. We haven't talked about this syntax too much, but for now, just think of it as I'm putting 0 into N1, 0 into N2, 0 into N3. #7 means wait 7 gate delays, just to make sure we can ensure that simple is going to produce the correct output. And then we call display, which is very much like printf. And now, in case you're not used to printf, if you're calling a Verilog function, you start with a $sign, so $display. X equal %d means that take the next argument and %d means a decimal number, put it in here. So it's going to take the decimal value of x and put it right here. Then it's going to keep going y equals %d, take the decimal value of y and put it in here. And then end means go ahead and end the simulation. All right. So we're going to put zeros in. What's x and y going to be? And 1 and 1. All right, let's go over here. Let's go send that to the background. All right. Sweet. Okay, let's actually I should have done this too. What could we do to change those values? 1, 0, maybe, yeah, put a, well, if we make the C, which is in 1, a 1, that'll at least make the Y a 0. And then 1, 0, 1. Actually, we'll make them all 1s. Let's see what that does. We did all 0s, let's do all 1s.
You need the gate delay on the second one?
Good catch, because I'll very show what happens if you don't. Because if I save this, and then I run, or compile and run, it says the same output. And as Perry pointed out, we didn't put the gate delay. Again, very important you put the gate delay after you assign the register values. We'll go and put in 7, Control S. And now it actually comes out because we waited for it to saturate. Okay, how are we doing? Please test your code. If you come to me and your module doesn't work, I'm going to ask for your test cases. And I will also ask for your diagram. But please, well, at first I'm going to give you the diagram, so you won't have to draw that. But those are the 2 things I'm going to ask for. Write your test cases, come to me, we can go from there. Okay, let me